Welcome to my YouTube channel. In this playlist, we are talking about operational amplifiers, and today we are going to discuss about half-wave rectifier designing and analysis using operational amplifiers. So let's start the video. In this video, we'll be discussing the behavior of half-wave rectifiers. Then we will design and discuss half-wave rectifier using op-amp, and then in the last we will design precision half-wave rectifier circuit using op-amp. So let's start the topic. What are half-wave rectifiers? Basically, half-wave rectifiers are used in voltage regulator circuits. Voltage regulator circuits are basically those circuits which provide you constant DC voltage. So these are basically used for all kind of circuits which are sourcing DC voltages. Now coming to the basic property of half-wave rectifier. Half-wave rectifier converts AC signal or alternating signals to pulsating DC signals or direct current signals. So there can be two types of half-wave rectifier. Either they can block negative half of the sine wave, or they can block the positive half of the sine wave. So to design these half-wave rectifiers, generally designers use one diode and along with that a resistor. Of course, you can design it in multiple ways, but in general, the minimum number of components required to design a half-wave rectifier is a diode and a resistor. Last but not the least, half-wave rectifiers are very less efficient compared to that of full-wave rectifiers, which we will cover in the coming videos. Generally, the half-wave rectifiers can provide up around 40% efficiency. Now, coming to the behavior of the half-wave rectifier circuits. So here in the right side, we can see I have drawn a circuit which is half-wave rectifier circuit. So to understand the behavior or working of this circuit, we have to assume few points. So remember, to understand the circuit, we have to have the knowledge of the switching of diode D1 and D2. So diode D1 and D2, please keep an eye on the polarities of these diodes. Here you have the P, N, and here you have the P and N. Okay, so we have to have the knowledge of switching of diode D1 and D2. Along with that, we must also know the basic behavior of operational amplifiers. In that, like I discussed in the previous video, you have to have the knowledge of virtual ground property and the property that the amplifier can generate an output which is maximum, which can maximum arrive up to plus VCC and minus VEE. We cannot go beyond that. Okay. So we can design, like I said in the previous slide, we can design either negative half clipped half-wave rectifiers or positive half clipped half-wave rectifiers. So the output that you can expect from a half-wave rectifier is like this. First one, positive half-wave rectifier, where you get the positive half of the sine wave, or you can design negative half-wave rectifier in which you will get negative half of the sine wave in the output. Now let us try to understand the working of this particular circuit. So here we have the half-wave rectifier using two diodes, in which suppose if we provide a positive voltage at the input, the output will try to become negative. Why? Because the input is provided to the inverting terminal. So inverting terminal, or you can call inverting amplifier, always generates an output which is 180 degree out of phase compared to that of input signal. So that means if you provide positive voltage, you will get a negative voltage. So when you have a negative voltage at this terminal, then if you can recall the polarity of the diodes, so N is getting negative, and P, by virtual ground property, this node will be becoming 0 volt because pin number 3 is grounded. So this diode D1 becomes short circuit, and the diode D2, which was connected like this, okay, here the P is getting negative voltage and the N is more positive compared to that of P. So that means this will D2 will act as an open circuit. So the resultant circuit will look like this when we apply a positive voltage. So in short, we can say for positive input voltages, the output tries to go negative, and this turns on the diode D1 and turns off the diode D2. Okay, turns off means making it open circuit. Now coming to the next half, that means if you apply a negative voltage, the whole circuit will behave in an opposite way. That means the output will try to become positive. So this terminal become, or this node will become positive, and you can now again correlate the behavior of diodes. So here the P is getting positive, N is more negative compared to that of P, and in this N is getting positive voltage and P is more negative compared to N. So that means the diode D1 will become open circuit and D2 will become short circuit. So the resultant circuit will look like this. Okay, so in short we can say for negative input voltages, the output will try to go positive, and that will turn the D1 short circuit and D2 to act as an open circuit. Or we can say the diode D2 turns off and D1 turns on. Now, in the previous circuit, this circuits, the disadvantage is that we will always see an output which is actually affected by the threshold voltage of the diodes. So you can never reach, or you can never obtain a 0 volt at the output of the half wave rectifier. What does that mean? Like that means if I am designing a half wave rectifier, then I will not be able to achieve 0 volt in this case. Okay, I will show you in the simulation. To achieve more precise behavior of half wave rectifiers, we can design precision half wave rectifiers in which we will use one diode with the output, and it comes in between the feedback path of pin number 2 and pin number 6. So we just have to add one diode at the output of the circuit. This will act as positive half wave rectifier, whereas if you want negative half wave rectifier, you just have to turn the diode in opposite way, or you have to just connect it in opposite way. So here you have the P at the output, N, which is connected indirectly to the pin number 2, and for negative half wave rectifier you have to connect N to the pin number 6 and P to the pin number 2 via feedback path. So advantage of this circuit is that we can obtain an output with no voltage drop due to the diode's threshold voltage, or we can say due to breakdown voltage of the diode. This circuit can rectify very small voltages, even smaller than 0.7 volt or whatever is the threshold voltage of the diode. So even you can rectify signals which are less than the threshold voltage of the diode, which was not possible in the previous circuit. And apart from that, the rectified output Vout can be amplified if required. So you can connect resistors so that you can generate amplified outputs if you require any amplification in the Vout. And by virtue of op-amp property, the output impedance here, okay, here is always very low. Okay, so these properties we can achieve from precision half wave rectifier. So let me show you how to analyze or see the behaviors of these particular half wave rectifiers and precision rectifiers. So in this circuit, I am applying 100 Hz 1 volt peak, or you can say peak to peak 2 volt signal to the input of inverting amplifier. You can see here the input is connected to pin number 2, therefore it is an inverting amplifier. And pin number 3 is grounded, so that means this node, pin number 2, is virtually connected to ground. Now let us see the behavior of this particular amplifier. So here you can see we are obtaining a rectified output. Okay, if you need to amplify the signal, you just have to change this particular ratio, because you remember the gain of inverting amplifier is nothing but minus RF, that is feedback resistance, by input resistance R1. Okay, so let me show you here. If I want to increase the gain, I can just make it 5k. So the gain is 5 times. You can see the output has been amplified. Now, what is the disadvantage of this circuit? You can see here we still are getting somewhere around 534 millivolt when the output is going negative. So this 0.5 volt is due to the threshold voltage of the diodes D1 and D2. So this is the disadvantage, that with this circuit we cannot achieve output less than the breakdown voltage of the diodes. Okay, let me show you another circuit here where I am applying a DC voltage, okay, in the input. In the previous circuit we were using AC. Now in this we are using DC. So the DC, I am here applying the DC voltage via VCC and VEE. So the voltage at this node DC V in can go up to plus VCC to minus VEE. Okay, so let me just simulate this part. You can see in the input voltage we have 1 volt, 1.43 volt, okay, at the input, and at the output we are getting minus 7.13 volt. Even though we are applying a gain of 10, so the output should have been 1.4 volt if the input, then we should have obtained at least 5 times gain of 1 volt. So let me just try to change the voltage. Okay, so to change the voltage I can use key A. So let me just change the voltage. If I apply 1 volt, you can see in the input I am right now applying 1 volt, precise 1 volt, and I am getting 5 volt at the output. Okay, but this is inverting amplifier's behavior. So we can change the gain by changing the R5 and R1. Now let us understand the behavior of precision op-amp. Precision half wave rectifier. Here I am applying AC signal which is 100 Hz. Okay, 100 Hz. And suppose if I apply 1 volt peak or 2 volt peak to peak. Okay, or let me go for higher voltage, 5 volt, because this circuit is unity gain amplifier, or you can say this is non-inverting amplifier with unity gain, because there is no gain provided to this particular amplifier. Now let us see the behavior. So in the output you can see we have 5 volt peak to peak input voltage, okay, because this is blue in color, whereas if you observe the output, you can see the output is red colored 5 volt peak. Okay, so there is, in this case you can see, even if I just try to show you here, the voltage is not less than, that means even the voltage is not affected by the diode's threshold voltage. So the output, when it is the input is going negative, we are getting minus 1.7 millivolt, which is basically due to the offset voltage of the op-amp. But otherwise, it is still far less than 0.6 volt because the output is only affected by 1 millivolt. Whereas if I try to design an inverting or negative half wave rectifier, in that case you can see here we are applying a sine wave, pure sine wave at the input Vin, which is represented by blue color, and at the output we can see we are getting negative half of the sine wave. And again, due to the behavior of this circuit, you can see here the positive half is not affected by the threshold voltage of the diode, because here you can see we are getting somewhere around 317 microvolt, which is almost 0 volt and far less than the threshold voltage of the diode. So if you plan to design any half wave rectifier using op-amp, then prefer precision half wave rectifier, because you can get an output which will not be affected by the threshold voltage of the diode. With this, I would like to end this video. If you have any doubts, suggestions or comments, you can post them in the comment section. If you like this video, then please do share with other fellows or other friends, and do subscribe my channel if you have not subscribed it yet. Thank you and have a nice day.